recording. Okay, welcome to Thursday, December 3rd, our class session, and I've got some interesting images to show you here. First, we'll take a quick tour of the website just to make sure you're oriented. In our class 119, we are finishing here in week 14. We're going to talk about, inverse functions and logarithmic functions. So we did several examples of quadratic functions last time. I want to show you one more visual. And we introduced exponential functions. And we gave you the speech for chapter 9 that we want to learn this one new shape for a particular reason. And you say, what do you mean one new shape? There's two new shapes. But the exponential function and logarithmic functions are inverses of each other, mirror image. So it's really one shape that we're using the mirror image of. Okay, definitely look at those problems. Thank you. And then we'll have a much better idea of what we can apply these functions to. So let me write down your questions. Let me give you just the basic outline here. We're talking about exponential functions. Inverse functions. And then we're going to introduce logarithms. And logarithmic functions. And two questions you want to look at. Let's take a look at 8, 7, 30, and 37. So those are questions about quadratic functions and applications of quadratic functions. Okay, just to make sure you know, focused on what's ahead of you this week, you just submitted homework number 10. And the solution that is posted, if you want to read that, by the way, it doesn't hurt to look at those solutions. Here's homework number 11, due next Wednesday. Then one more written homework and you're done. You did the XYZ homework through 8-6. Now back to just 4 sections here in 8-7, 9-1, 9-2, and 9-3 for next Wednesday. Okay, that's what's currently due. Okay, so now let's take one of your questions here just to open it up and warm up this morning. 8-7-30, 8-7-37. I had actually picked out 8-7-30. I thought that was a good one. Didn't have time to share it. 37 is exceptional. Okay. So even if this slows me down a little bit, those are two excellent questions. So let's do them. And you know, kind of the fun, excellent paradox of this is you ask a question, and then you get the feeling that that kind of slows this down. We have room to adjust our schedule even in these very late stages of the semester. But the funny, useful benefit is by doing these, you actually learn how to do stuff faster. So it's the opposite of slowing us down. It's kind of speeding us up because you'll be quicker at doing these problems. So let's look at number 30. And instead of pulling this up on the screen or pulling this under the camera, You can go to the problem yourself, but I'll just outline the problem if you want to check it later. You want to read the actual problem. I'll just write down the key notes right here with this problem. So it says the owner of a used bookstore charges $2 for a quality paperback. That sounds about right. And usually sells about 40 a day. But she notices that she increased that by 10 cents. $2.10, $2.20, $2.30, $2.40, $2.50. She thinks that they will sell too fewer per day. Maybe they've got experience playing with the price. Maybe that's just their best judgment. But the idea is sound. If you raise the price, you're probably likely to sell less of the quantity of that object. So if this is the case, what price should she charge to the nearest 10 cents for these books to maximize her income? What would that income be? Now, by the way, this is just a guess that she's making about her bookstore material. If she tries this out for a couple of weeks and it doesn't work, what will she do? Refine her guess, adjust her guess, change her model. That's how a math person would say it. So we have the number of books sold. Let's make some notes. We have the price per book. That's a dollar amount, dollars and cents. And then we have the income. And this income is daily income. Number of books sold daily. Price per book that you set each day. You could change the price, and the income you make daily. So let's set some variables for these, because we got to go from words to formulas, words to equations. Number of books sold each day. Let's call that X. Price per book, we can call that P. And income, another word for income is revenue, fancier word. Let's call that R. Okay. If she charges $2 for a book, she sells 40 in a day. So this is near the end of this section for a particular reason. They are not going to give you any of the formulas. In some of the previous problems, they were actually giving you formulas. Formula for how X and price are related. They're going to make you construct all the formulas. That's why this is such a good problem. So if the price, I don't know whether you want to call it price and book sold or book sold and price, you could literally do it either way. And this is a part of what we're going to talk about today when I talk about inverse functions or inverse relationships. Regardless, sells $2 for a book. That's the price. She expects to sell 40 books a day. And then she says, if I increase that by 10 cents, that would be $2.10. She expects to sell 2 fewer books per day. So at $2.10, she thinks she's going to move 38 books. And we could go on and on with these numbers. 20 cents, 36 books, 2.30, 34 books. Why don't I just pick one more number down here? What happens if she chooses to sell the books for $3 each? So she did 10 dimes more. She increased the price by 10 cents 10 times. Every 10 cents, she loses 2 books. So if you increase it by a whole dollar 10 times, you're going to lose 20 books. This at least is what she's thinking. Whether you say it 20 books at $3 each, or setting the price at $3 gives you 20 books. This is just a bunch of information, but now it's gonna let me write an equation. I want an equation. So let me make a very crude graph right here. Let's call that 2, 1, 2. I'm just doing sketch work almost. Let's call that 3. Let's say that this is the price of the books. $1, $2, $3. Over here, let's put the books sold every day. And if you set the price at 2, you get 40 books sold. Let's just mark this casually as 40. And if you set the books at $3, you get 20 books sold. That's way down here. I'm trying to draw a responsible scale. This is a pretty good scale. And every time I increase by 10 cents, I drop 2 books. This equation is a line. Eventually, if she sets the price too high, another $1, she'll lose another 20 books. If she sets her paperbacks at $4, she's expecting possibly she won't sell any books. If she sets it at $5, she'll sell negative 20 books. That's not good. I can't sell negative 20 books. But remember, this is just shooting in the dark. This is just a model. This is just her guessing where to set the price. So can I find the equation of that line? I'm going to use the point slope form way back in the old days. 2 and 40, 3 and 20. What is the slope of that line? I went over 1 unit, $1, and I went down 20 books. So the slope of that line is minus 20. I lose 20 books for every $1 I increase the price. Got a base point on that line? Sure. Let's take the base point to be 2 and 40. Now I'll use this formula to give me the equation of the line. Now, I'm a little bit of trouble right here. I think I should make an adjustment because I usually think of lines in terms of y and x, but this is p instead of x instead of y. So I maybe should write this line like this. X minus x naught equals m times p minus p naught. I should write this point 20 and 40, not as x naught, y naught, but as p naught, x naught. Okay, let's go. Take that number into this equation. X minus x naught 40 equals minus 20 times p minus p naught 2. Let's solve this equation for x. Negative 20p plus 40. Negative 20 times negative 2 is plus 40. Then I'm going to add 40 again, plus 40. This line is negative 20p plus 80. That describes the number of books I sell for the price I set. Do I have the right line? Let's try a 3 in there. What if P was 3? What does that predict? If P is 3, this is negative 60. 80 minus 60 is 20 books sold. Yes, that matches my line.
What does not mean?
Can you say that again?
What does not mean? Like you were saying, like P naught, X naught.
Good. This is a slang. I should be more careful how I use that. When someone says X sub 0, like this is a special X, or P sub 0, this is a special P, this is my base X, this is my base P. They pronounce it, and they could pronounce it X0 and P0. Sometimes they pronounce it X naught. Naught is just an old-fashioned word for 0. If you got naught, you got nothing. It's an old-fashioned word for 0 or nothing. So it's just my base point that I was using right there.
So it would be interchangeable with like X minus X1 and Y minus Y1.
Sure, I could have wrote that X minus X1 equals M times P minus P1. You can name this point anything you like as long as you insert it correctly into the formula.
Okay.
Now let's go for equation of revenue. Based on the books sold or revenue based on the price? Let's think about this. The revenue in English is going to be number of books sold times dollar price per book. So if I have price P for the book, how many books am I going to sell? That's X, number of books sold. I've got this nice formula for X. Minus 20p plus 80. So now I know my income, my revenue, based on the price I sell each book at. And if I write this by multiplying it out as a parabola, I get minus 20p squared plus 80. Now it's either time to graph this or it's time to go for the vertex. I'm going to just go for the vertex, then I'm going to graph it. 80p, excuse me. What's my formula for vertex? Minus b over 2a, c minus b squared over 4a. So this is a parabola that opens upside down. That minus 20 tells me upside down. I want to know this high point. That high point is my maximum revenue, maximum income. So what's A? Minus 20. What's B? 80. C here is really 0. There was no constant left. There was nothing but p squared and p. So minus b, negative 80 over 2 times negative 20. Negative 80 over negative 40 is 2. And what's c? 0. What's b squared? B squared is 6,400. 80 times 80. 8 times 8 is 64. 8 tens times 8 tens is 6,400. Divided by 4a minus 80. How's that number come out? 2 negative divided by negative is positive. Cross out one of the zeros. 640 divided by 8 640 divided by 8 is 80. Now we're going to put that into a graph. But what I've just learned is that the top of that parabola is when P is 2 and I will make $80. And apparently that is the best I can do. Now let's try it by graphing this parabola, and let's graph this parabola in Desmos. So let me open up a Desmos window and then I will share it with you. Let's put in this formula. Sometimes Desmos is picky about letters, but it allows you to type in formulas directly. So let me see if it allows me to say P. It does. It does allow me to graph P. Now, this is, if I go way, way up here, an upside down parabola. But I think what I need to do is make a window that goes all the way up to 80 for my vertical axis. Notice it doesn't say the P axis or the R axis. Let's just say go up to 100 from -10. Now, how about my X axis? The X was, well, the horizontal axis, the price axis too. Let's check that I sell my books from 0 cents to, I don't know, $3. This interesting thing right here, the step function. I could mark every 10 cents. Oops, and see what happens. Now, this is only part of a parabola. Do you see that from 0 to 3? Maybe I should make this bigger. Let's make the x-axis -1 to 6. Okay, maybe that's bigger than I need, but here is my maximum. If I sell books for $2, I will make $80 in profit, income, because I'll sell 40 books at $2 each, be $80. But what if I want to change that price and you see Desmos says, do you want to add a slider for price? Okay, let's add a slider for price. Let's price my books from 0 cents to, well, $0 to $3. Nope, 3.0, $3. And let's step every 10 cents. Let's see what else I can do here. Let's add a label to that book. And the label is revenue. What happens every time I charge another 10 cents? At first, I'm making more revenue. P is 1.4, that's $1.40. Oh, good, let's add 10 cents more. $1.50, I'm making more money, let's add 10 cents more. $1.60, I'm making more money. But there is a point of no return, $1.70, $1.80, $1.90. After I hit $2, this is for her original book price. Now I add 10 cents and I make less money. It's kind of paradoxical, right? But I make less money because I sell less books, and it's only slightly less money. When P is 2, you see that the revenue in the box below is $80. Next time I make $2.10. Okay, now the revenue is $79.80. I might not even notice that, but every time I add 10 cents now, I sell less books and I make less revenue. See, back here when I was way under pricing, I was selling my books for $1.20. I was making money. but I was underpricing my books. So I started adding to the price of the book and I started making more money, 72.8, 75, 76.8. And then I get into this trap saying, oh, I'll just keep raising the price of my books and I'll make more money forever. Well, of course, logically that doesn't make sense. After I pass that $2 mark, people start looking sideways at me and saying, charging $2.50 for a book? I'm going to go somewhere else. I start making less revenue. So it's kind of an interesting demonstration that you can raise your price to make more money to a certain point. And then beyond that, raising your price doesn't make you money. It loses you money. You think of that as a natural thought, but this is like showing that natural thought with a math calculation. Okay, very good. I'm going to do the other one because the other problem you asked is also excellent. And it matches with what we just did, number 37. Got that one? Let's do that one. 37 says, find the equation of a quadratic function in standard form passing through the points minus 4, 5. So instead of showing you the problem again, let me just read this because it's even shorter than the last one. These would be great review problems too, by the way, when we reach our review session in a week or so. Find the parabola, find the quadratic function, that's the parabola in English, that goes through these 3 points, minus 4, minus 5, minus 1, minus 8, and 2, 7. How are we going to do that? And a little video lag there. Let's think back to the last problem. In the last problem, I had 2 points, and I knew that that generated a line. And probably you've heard this saying before. Get my paper straight. 2 points makes a line. They don't mean that a line is only made out of 2 points. They mean that if you give me 2 points, there is only one line that goes through them, and I can find it based on that equation, whatever you call the letters there, but based on that equation. But you may not have heard this saying. 3 points makes a parabola. And I'll show you how. At first, that sounds crazy. Like, I pick out any 3 points and you give me a parabola? Okay, smart person, give me the parabola through those 3 points. Well, it's going to take a little creativity and it's going to take some calculation, but I'll show you how to do it. How do I visualize it? What I have to visualize is something actually that's probably kind of tall. I mean, if you pick the 3 points in extreme locations, the parabola might be extreme. Let's say you pick the 3 points like this. And the parabola might be very flat. Let's say you pick the 3 points like this. The parabola might be so wide and flat that it doesn't even fit on the screen. But you can take this to the bank. If you pick 3 points out, there's only one parabola that goes through them. Now I'm going to make an exclusion. And it happened to do with the example we gave you last day with a ball flying in the air. If you pick 3 points out that lie in a straight line, I'm not going to allow you to say that's a straight up and down thin parabola. I'm just going to make you talk plain and say, it's a line. You made a line. So if you pick 3 points that lie on the same line, I'm not going to call that a parabola. But if you pick 3 points that don't lie on the same line, 3 different points, different locations, then you automatically get a parabola. And this requires something we did earlier in the semester. So let's draw a picture, and then I'll show you how to do the calculation. Since his points were kind of large, we got to draw a kind of large picture. So -4 and -5 was right here. The 3 points are right here. How about -1 and -8? I'll add some scale here in a second. That would be right there. Last point, 2 and 7. It's point 2, 2, 4, 6, 7. So how am I going to find the parabola that goes through those 3 points? Let me darken them up. Let me add scale, and then I'll show you how to calculate. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. This seems like a convenient scale. 2, -4, -6, -8. Okay, so we got a good handle on that picture. And if our drawing wasn't good enough, we'll go to Desmos. We will go to Desmos to check it. Here's the logic we're going to use. I could write down these names here just so you see them. I know that every parabola written in standard form looks like this. The only trouble I have here is I don't know what the A and the B and the C are. This work we're going to do here even relates to what we're doing today. How could I find the A, B, and C? Let's think like this. If I need to find 3 things, as a general rule of thumb, is I'm going to need 3 pieces of information. And I have 3 pieces of information. My parabola goes through these 3 points. The only question is like, how do I use this information? But think of each of these points as an X coordinate and a Y coordinate. So for example, if my parabola goes through 2 and 7, that's saying that if I stick in X equals 2, I better get Y equals 7. That looks like this. Putting in a 2 gives me A times 4, B times 2, and C. Do you see that that gives me an equation? 4A plus 2B plus C equals 7. There's one equation with 3 unknowns. But the other 2 points also give me equation. Now I got to be careful with all the minus signs. But what are the other 2 equations? If I put in -1, I better get -8. Let's put in -1 to this equation, -1 for x. That'll be 1a minus b plus c equals -8. Okay, 2 equations, 2 unknowns. You remember doing this? Linear equations, linear systems. Let's try the last point. If I put in -4 for x, I better get -5 output for y. Let's put in the -4. 16a's minus 4b's plus c equals -5. I'm gonna have to move to another paper now. So we'll come back and draw. These are 3 equations, 3 unknowns. You got to read way back, probably in chapter 3, and say, I know how to solve this to figure out what the A, B, and C are. So I'm going to have to go to another paper. And I'm going to copy it over so I don't have to have 2 papers on the same screen. I will copy it over in a way that helps me. In other words, I'll put the simplest equation first. Then the 4a plus 2b plus c equals 7. Then the 16a minus 4b plus c equals -5. Now you got to remember how we did this. What did we say? We add multiples of one equation to the other. So if I say -4 times the first equation and add it to the second equation, what do I get? -4a plus 4b minus 4c equals 32. That's -4 times the first equation. Let's add it to the second equation. 4a plus 2b plus c equals 7. Now make sure you multiply exactly correctly and with all the minus signs accounted for. What I get is 6b's minus 3c's equals 39. In fact, I can make that a little bit easier on the eyes by dividing everybody by 3, since everybody is divisible by 3. 2b minus c equals 13. Okay, there's one equation. Now let's kill this 16. Like I killed that 4a. Let's eliminate that 16. Let's take -16 times equation 1 plus equation 3. -16 times equation 1 is -16a plus 16b minus 16c. Yuck, -16 times -8. I got to think about that. 128 positive. Negative times negative. 8 times 16. Let's add equation 3. Equation 3 is 16a's minus 4b's plus 2c's, plus 1c. Be careful how you copy. It's -5. What do I have? No a's. 12b's minus 15c's and 123. Notice I also catch a break. This is divisible by 3, every number. So I could write this as 4b minus 5c. Sorry, move the paper up. Is 41. Each one of these divided by 3. Let's call this equation b. Now, a little bit of shell shock here, right? But do you remember you did this once? You can never forget anything, really. You got to say everything adds up. Let's finish this by getting rid of b. Why don't we take -2 times equation a and add it to equation b? negative 4b plus 2c equals negative 26. In fact, if you remember, we also gave you a way to check this on your calculator. 4b minus 5c equals 41. So I have no b's, minus 3 c's is 15. C must be minus 5. If c is minus 5, I can go back to this equation. Sorry, I keep forgetting to move my paper up. If c is minus 5, then minus 5 is 5. 2b plus 5 is 13. Subtract 5. That means 2b is 8. That means b is 4. Now let's go back to the very top. If c is minus 5 and b is 4, the negative 4 and negative 5 make a negative 9. Add it to the other side. Negative 8 plus 9 is 1. So a must be 1. And guess what? Now I found the parabola that goes through those 3 points. It's not even a nasty looking one. It's just an ordinary looking parabola. Now you're going to say, no way. You're going to look at these 3 points right here and say, no way. How do you know it goes through those 3 points? Well, I could draw it very carefully, or we could just put that on Desmos. Let's put those points into Desmos. Let's put that parabola in Desmos, and you see the parabola go through the points. Let's try it out. I got to make sure I got everything together. Let's share screen back to Desmos. So I like this little illustration here, but I'm going to dump it. And let's type in these 3 points I was given. Minus 4, minus 5. Minus 1, minus 8. 2, 7. Oops, need the parentheses. 2 comma 7. Sorry. I see the 2, 7, but what's going on here? I'm way off scale, right? It must be badly off scale. Where's the minus 4? Oh, it's way over there. Okay, so let's get back to a normal scale. My drawing was minus 8 to 8. Why don't we try minus 10? Whoops. Why don't we try minus 10 to 10? And same for y. Get rid of that 0.1 I was using the previous problem. Okay, better. You see these 3 points here right now? They really look disconnected. But now let's type in the parabola. It's even hard to see the parabola going through there. But let's type in the parabola we found. X squared plus 4x minus 5. And what happened? It's almost like a miracle. There's the parabola that goes through those 3 points. It's centered at x equals minus 2. And you could find the vertex of minus 2 and minus 9 just by using your vertex formula. But you wouldn't have believed, you might not have believed that those points would go through one parabola. That is the only parabola in the universe that goes through those 3 points. That was a great problem to practice because it used that old thing we learned a while ago. Called a linear system of equations. That was so good, I probably would have picked that to be a test question. Maybe I still will. Now, if you want to see it done again, he does this also in an example in that section. So you want to try this on your own, kind of, with someone's work next to you. Look at this example 10 in section 8.7. He does it again with a different 3 points. So you can practice it again. Actually, this is not a bad skill. It's kind of important that if someone gives you a list of points, you should be able to fit a line or a parabola to those points. Now, what if someone gave you 3 points that didn't line up and told you to draw a line through them? Well, first of all, you'd say, I can't draw a line through them. They don't line up. But is there a best line you can draw through them? The answer is yes, there is, and you'd be likely to see that in a statistics class if you want to take a statistics class next semester, where you use a lot more algebra, but you get to do a lot more practical problems. So you can do this problem with any number of points and say, even though 2 points makes a line, what happens if I give you these 20 points? What's the best line that goes through those points? Okay, we're getting to the top of the hour, but these were 2 great questions, so it was worth it. Let me give you a little setup for what we'll do today, and then we'll take a break, then we'll come back and get to work. Pens out of the way here. I gotta make sure I'm keeping track of my papers and numbering the papers. If you want to go and read this work again. Put those aside. But let me set up this topic of inverse functions and logarithmic functions. We drew a couple exponential functions last time, and maybe we'll draw some more today too, or draw some more over the next couple days. But what does it mean to be an inverse function and a logarithmic function? What are inverse functions and logarithmic functions? Let's go back to that book problem. And the line I created when I said, if I charge $2, 200 pennies, I will sell 40 books. And if I charge $3, 300 pennies, I will only sell 20 books. And in the picture I created, and I'll copy the picture here, I also said to you, well, if you like, we could look at it from the other way around. If I sell 40 books at $2, and every 10 cents loses me 2 books, then if I drop to 20 books in sales, if I drop 20 books, I lose 2 books for every 10 cents I add to the price. 10 times 2 books, I must have increased the price by 10 dimes. I must have been charging $3 per book. Now, I constructed a formula in that example we did that said X is equal to minus 20 times 80. I'm sorry, minus 20 times P plus 80. And this meant that if I set the price at that amount, I will sell that many books. But I could turn this formula inside out. This is a formula for the number of books sold when I set the price P. What if I turn the formula inside out and say, let's solve for P? Well, it's not a hard thing to do. To solve for P, minus 20P plus 80 is equal to X. You'd subtract 80 from both sides. And then you divide everybody by minus 20. You could say P is X over minus 20 plus negative 80 over minus 20. Negative 80 divided by negative 20 is plus 4. You could say P is, if you want to think in terms of a line, minus 1/20th X plus 4. And this is a formula for the price you're charging if you sell this many books. This is a formula that literally says, if I sold 40 books, 40 times minus 1 over 20 is negative 2. 4 minus 2 is 2. If I sold 20 books, I must be charging $2. If I sell 40 books, I must be charging $2. If I sell 20 books, 20 times minus 1 over 20 is negative 1. 4 minus 1 is 3. If I sell 20 books, I must be charging $3. So these two functions are kind of like undoing each other. This function is X in terms of P. This function is P in terms of X. And I could draw those two functions. The numbers are kind of large, so it's kind of hard to fit them on the same graph, especially if I'm talking 1/20th and 4, minus 20 and 80. All right, could I fit those on the same graph? Let's call this 80. Let's call 4 boxes 80. And let's try to draw this graph right here. Let's also make this 80. Give me another point on this graph. If I plug in P equals 4, I get X equals 0. Where is 4 on this scale? It's got to be a 20th of the scale. This is 40. 4 is a 10th of that. 4 must be about right here. This is a terribly difficult line to draw. Almost perfectly vertical. Almost perfectly vertical. Let's draw this line. That's even harder to draw in this picture. It's got an intercept of 4, and it increases by 1/20th, or it decreases by 1/20th every time I change the x. If I made x 80, this would be equal to 0, and I'd get this line. I almost want to graph that on Desmos for you, and then we'll take a break. But I cannot draw with my hand this beautifully. What I have here with these two lines is two lines that are exact mirror images of each other. These two lines that I draw, the one that's almost vertical and almost flat, are mirror images of each other across this mirror y equals x. Let's draw that in Desmos. We can take a break here. Let's draw y equals minus 20 x plus 80. Now let's do a super zoom out. You see it crossing right there at 0 and 80 and at 4, 0. Now let's do that equation backwards. X equals minus 1/20th times y plus 4. I'm sorry, let me keep the letters y and x. Now I've done a super zoom, and maybe if it'd be better if this one was red and this one was orange. Maybe it's red and orange. Okay, good. Sorry. Thank you for pointing that out. Did I share the screen properly? No. Okay. Let's run it once again. Here I typed in the equation minus 20x plus 80, y equals minus 20x plus 80. And here I typed in the equation y equals minus 1/20th x plus 4. You say, what'd you do with the x's and the p's? I just say, I want to use the same letters in both just to see what happens. But what I want you to see in this red line and green line, even if I zoomed in, what I want you to see is this red line and green line are like a mirror image of each other across the line y equals x. I want this to be dotted. Desmos has changed its graphing. That's interesting. It updated this little graphing thing here, right? So I don't know what that means if I change that number, because I'd like to experiment. Put a black line in there. It made the dots smaller. That's interesting. And what about spacing the dots? Okay, I can't do this all the time. No, that's not. Let's play with this later. What I want you to see is the red line and green line are like mirror images across this dotted black line. That is, in plain English, what people mean when they talk about inverse functions. Let me go back to my paper. When two functions are inverses of each other, they are perfect mirror images across the 45-degree line y equals x. That if you turn them over, you couldn't tell the difference. Now my drawing right here is too slight and too poor. But in the Desmos drawing, you see exactly what that means. Here's a point called 0, 80. What would happen if I reversed the 80 and the 0? I'd get 80, 0 on the other line. How about this point, 0 and 4? What would happen if I reversed that point? I get the point on the other line, 4 and 0. Even this point right here, some kind of decimal point, 3.81 and 3.81, that seems to live on both lines. What would happen if I reversed 3.81 and 3.81? Well, I would just get 3.81 and 3.81 back. Whenever you have two graphs that are mirror images of each other, something special is happening. Let me show you this picture. Zoom way in here. I'll get rid of the clutter. Let's get rid of the red, the green. Let's make this red. And then let's graph x equals y cubed minus y. Let's make this one another color, blue. Look at those two graphs. Y equals x cubed minus x, and x equals y cubed minus y. I don't know what that looks like. Is it a butterfly? Is it a whatever? Is it like a psychology test? But this red curve and the blue curve, let me turn off the blue curve. There's the red curve. Let me do the blue curve. There's the blue curve. When I put them together, what do I get? They are perfect mirror images across the line y equals x. Like y equals x was a mirror, surface of a lake, surface of a quiet lake. Okay, I've gone way too far, but I got to come back and explain what it means for two functions to be mirror images. So let's take a small break here. So I'm talking, we've gone a little bit far today. Give you a full 5 minutes. And so to stretch your legs, let me get back to my paper. And then I'll show you more about what it means for two functions to be mirror images of each other. Okay, I'm going to mute my microphone. You just stand up, stretch your legs for 5 minutes, and then we'll come back and talk about this and the special logarithmic functions. Okay, back to work. There's something special about inverse functions. And I want to be able to create them and use them in very special cases. And the special cases I'm most interested in are things like lines, square roots and squares, cube roots and cubes. Those things are things that are naturally inverse. If we want to undo a square, we take the square root. And you and I call it undoing the square. If we wanted to undo a cube root, we would cube something. And we use that language. I want to undo the cube root. If I'm subtracting and I want to undo subtracting, I add. And we have been all through the class, even all through any of your math classes, you are constantly trying to unwrap, undo something that someone else has done when you're solving an equation. So the process of undoing something is then, that's a process I want to understand. That's a process I want to study. So let's say I gave you a function and I want to study it for lots of different functions, not just for basic functions. But let's start out with a basic function. Let's say I want you to find the inverse. I like these lines right here that we just did, but the numbers were a little bit extreme. The 80 and the 1/20th, those numbers were so far apart in extremeness, my picture wasn't very interesting. Let's try some more plain numbers. Let's find the inverse of the function y equals 2x minus 4. Don't forget, you can always write this function, this linear function. This is literally a line. Just speak plainly, it's a line. You can write it as a function of x in a fancy way. This is a formal notation. F of x equals 2x minus 4. So we've talked about both ways of writing this. This is just a little fancier way to write it. So what would it take to undo this equation? What would it take to turn this equation inside out? Literally, instead of y is a function of x, I'd like to find out what x is based on y. I would like to rearrange this equation so that I have a formula for x. And that's not hard to do. I will add 4 to both sides. And what did I just do? I just undid subtraction. I undo subtraction by adding. I will divide both sides by 2. Again, that's not hard to do. Although I might want to say to myself, should I use 1 fraction or 2 fractions here? Let's split it into 2 fractions. X, 2x divided by 2 is single x. Y divided by 2 is 1/2 y. And 4 divided by 2 is 2. Now I haven't changed the original function, I've just rearranged it. Now I've written x as a function of y right here. It's a different function than the original. The original function says take x, double it, subtract 4. This new function says take y, cut it in half, and add 2. But I want to emphasize that mirror image thing that happened to us. So I can draw this both on one graph. Let's exchange the x and y. So I write this not as x equals 1/2 y plus 2, but y equals 1/2 x plus 2. What I want to show you is by switching the x's and y's and solving for y, or I could say solving for x and then switching the x's and y's, either way. I want to show you that I've created two functions that are mirror images of each other. Let's go to the graph. Here's some beautiful mirror images. Maybe we'll do some wiggly mirror images later. But let's just start with simple mirror image. Y equals 2x minus 4. And let's expand out a bit. Whoops. That's interesting. My browser just went kaput and shot out from under me. So I'll get it back. But I got some idea what happened. So let's share the window again. Okay, y equals 2x minus 4. And let's zoom out a little bit so I can see that line. And do you see my units are 1 to 1? This is nice square box, 5 units wide, 5 units tall. What was the other equation? Y equals 1/2 x plus 2. Are those functions mirror images of each other? Let me add the mirror, then it's easier to see. Let's add the mirror. Let's add the mirror with black dotted lines. And then we can zoom in a little bit if you like. Yeah, that red and blue line are mirror images of each other, no matter how far you look. If the blue line goes through 0 and 2, the red line goes through 2 and 0. If the red line goes through 0 and minus 4, blue line goes through minus 4 and 0. Literally switching the x's and y's as I did on my paper. Here's a special point where they both meet at 4, 4. But even that shows the mirror image. What do you get when you take the point 4, 4 and you switch the x's and y's? You get the point 4, 4. It lives on both lines. How about this point? 5, 6. It's hard for me to pinpoint that. Hello. It's not going to let me pinpoint that, so I will draw it. 5, 6. Right there. And then next to it, let's draw 6, 5. Immediately on the other side, just switching the x's and y's. So you're going to ask them the question right now. You're going to ask the question like, why do I care about mirror images? Why do I care about inverse functions? Well, I'll try to help you care. But first, let's look at the procedure. If you want to find the inverse of a function, this is what you do. You turn it inside out. you solve for the x instead of the y. And then you switch the letters x and y so you can graph them on the same axes. Now, some people write it like this, that fancy notation, f of x equals 2x minus 4. And they also have a fancy notation for the inverse function, and they call it f inverse of x equals 1/2 x plus 2. That inverse does not mean reciprocal. It just literally means the inverse or mirror image function of f of x. So you got to get used to that notation. If people are being formal, they use the notation f with a superscript of -1 to mean f inverse. If you put these two functions together, let's take the function f and feed the function f inverse to it. Do you remember that word composition? What happens if you take the function f? 2 times blob minus 4. And you insert this function f inverse, 1/2 x plus 2. Look what happens. 2 times 1/2 is 1x. 2 times 2 is 4. And when you subtract 4, you just get x. You get back to where you started. What happens if you did it the other way? What happens if you fed the function f of x to the function f inverse? It's not hard to do. What does f inverse do to people? Cuts them in half and adds 2. Well, let's take f, which is 2x minus 4. Let's cut it in half, x minus 2, and then add 2. What do you get? You get back to where you started.
Hey, Professor, I have a question.
Go ahead.
So this whole time we were going on, -2 on one side, -2 on the other to keep the equation the same. So how is the equation still the same, but yet it describes different information?
Good. There was one point in our little speech here where I made the equation not the same anymore when I took the mirror image. And that was right there. These two equations are the same because you did just as you said. Add 4 to both sides, changes nothing. Divide both sides by 2, changes nothing. This box and this box are the same. The thing that made it mirror image was then switching the x's and y's between these two boxes. It's right here, if you will allow me to say this in English, that I took the mirror image, that I held one function up to the mirror to see the other. It's not until I switched those x's and y's that happened. And that's a really good question. So let's go back to Desmos and I'll show you. Let me turn off the inverse function. What would have happened if I had just typed x equals 1/2 y plus 2? Turn off the mirror. Turn off those points. Do you see the red function and the black function are the same? Maybe you can see them better the same if I made one of them dotted. Now the red function and the black function are exactly the same. When I solved for x, I did not change anything It wasn't until I solved for x and switched the x's and y's. This second box to the third box, all I did was switch the x's and y's. And when I did that, I took the mirror image.
Oh, okay, I see.
That is sneaky, but that is the way you have to think about it. That's how I found the inverse function. Let me try another one. And this is worth spending the time on. Let's think about this. What if I said to you, y equals the square root of x minus 2? We've drawn a couple square root functions. This square root function has moved 2 units to the left. We haven't spent.
Still sharing
Yeah.
your screen.
Good point. Thank you. So let's graph y equals the square root of x minus 2. It's like half a parabola on its side. In fact, we said that. It's half a parabola on its side. Starting, oh, I got to put a plus sign in there if I want it to start at minus 2. Adding 2 moves it 2 steps to the left. So let's take that and do just what I did on the last problem. Let's undo it. So y is not made out of x's. Let's make x out of y's. I will undo it first by squaring both sides. Then I will subtract 2 from both sides. And so far I have changed nothing. But if I switch the x's and y's now, orange doesn't show up. Well, it doesn't show up too badly, at least not showing up too badly on my camera. Switch the x's and y's. Now I've created a mirror image. It's a parabola that drops 2 units. Parabola follows the 1, 3, 5 pattern, and it drops 2 units. And it now looks like this. Now the problem is, you said you didn't draw a parabola, you drew half a parabola. Well, I wanted to draw the half of this parabola that made the mirror image. In other words, if I included the other half of the parabola, it wouldn't completely be a mirror image anymore. It would be kind of a mirror image with that side. So what do I have to think about right here? X plus 2, according to the rules, must be greater than or equal to 0. And if x plus 2 is greater than or equal to 0, then x itself better be greater than or equal to minus 2. And when I switch the x's and y's, that means y better be greater than or equal to minus 2. And you look at the orange parabola and you say, sure it is, no problem. But on this side of the equation, what can you say about y? Square roots only spit out positive numbers, right? Sometimes they spit out 0. So on this side of the equation, you have to say y is greater than or equal to 0. Yes. Y is still greater than or equal to 0 if I square both sides. So when I get down to the bottom and I switch the x's and y's, instead of y being greater than or equal to 0, I have to choose x greater than or equal to 0. I have to choose the right-hand side only, or I don't get a perfect mirror image. I could show that again in Desmos. I will. I'll share the screen with you because Desmos allows me to restrict the graphs in different ways. So if I say y equals square root of x plus 2, I get that square root graph there. And if I say x equals y squared minus 2, what do I get? A parabola sideways on top of the square root. But if I further say that y must be greater than or equal to 0, then that parabola is only the upper part. Now let me switch the x's and y's. How about y equals x squared minus 2? Sorry, equals x squared minus 2. That's a full parabola. But if I want to make the mirror image with this purple square root sign, I only want the part on the right. So instead of x greater than or equal to 0, instead of y greater than or equal to 0, I'll say x greater than or equal to 0. And that gives me just this side on the right.
So would that be how it would work the other way if you were doing square roots?
Yes, you would do it the same way backwards if you were doing square roots. I can put in the other side. It's kind of a faint shadow if you want to see it. Here, I put in the other side of that parabola as kind of a faint shadow if you want to see it. But the problem is I don't want to use both sides of the parabola because I want to create a mirror image. Why don't I want to use both sides of the square root? You say, why don't you keep both sides of the square root? I'm losing my way in typing these. Why don't I keep both sides of the square root and both sides of the parabola? Aren't those perfect mirror images? You say, sure they are. Kind of cute. It's kind of like a little, maybe like a heart upside down or something, or sideways. But the reason I don't want both sides of both of these parabolas is not because of the purple parabola. That's a beautiful function. This black parabola sideways is illegal. Why is it illegal? This is not a function. It doesn't pass the vertical line test. I can't use this sideways parabola as a function. So I erase the bottom part and I only use the upper part. I'll make it black for you. But that means I have to erase the left-hand side. If I want a perfect mirror image, I have to erase the left-hand side of this parabola. And only use the part where x is greater than or equal to 0. Now I got a perfect mirror image, and they are both legitimate functions. Okay, let me show you a special function now. So this process that we've been practicing is called creating an inverse function. And I could say it plainly in English, like this. Take the formula y equals f of x and solve it for x till you get x as some function of y. Then switch the x's and y's. And this function g of x is the inverse function of f. G is the inverse. Sorry, I got to go back to my paper. This is a process for creating an inverse function. You take some description. Y is some messed up combination of x's. You solve for x. Now you got x is some messed up combination of y's. You switch the x's and y's. And this g function that you created is the inverse function of f. At that point, you like change the name of g to f inverse. And you say g is f inverse. Or in English, you say g is f inverse. That's how you pronounce it in English. And I don't want to do this just when the function is a line or a parabola. I want to do this for any legitimate function. In particular, I want to do it for that funny function we introduced last time called the exponential function. So do you remember from last time what it means to say y equals 2 to the x? Let me draw a large scale picture here. Large enough to show the formula and the picture at the same time. Remember, we made a chart that said if x equals 0, 2 to the 0 is 1. I'll add scale in a second. If x equals 1, 2 to the 1 is 2. 1 and 2. If x equals 2, 2 to the 2 is 4. If x equals 3, 2 to the 3 is 8. 2 and 4, 3 and 8. This is kind of a funny graph. Does it look like half a parabola? Almost looks like a half a parabola unless you go and do the other half. Because if x is minus 1, 2 to the minus 1, remember what negative exponent means, 1/2. If x is minus 2, 1/4. If x is minus 3, 1/8. Those are just as hard to draw. If I to x is 4, I get y equals 16. Very hard to draw, it's off scale. But these tiny ones are hard to draw too, because first I cut it in half, then I cut it in half. If I keep cutting something in half, it'll get so small that I can't tell the difference between that and 0. So I'm not going to draw lots of these. I'll just draw these. And that's a good shape right there. What does it say? Shoot through the rough as I go out to the right. Flatten as I go out to the left. Technically, it gets so flat, it almost looks like that axis. There's nothing wrong with drawing that like that. As long as you don't draw below, it never goes below. 2 to the x is never a negative number. I don't care what x you pick. It always stays above. You know, an 8th, a 16th, a 32nd, a 64th, a 1/28th. 1/128 is tiny, but it's not negative. And no matter how many times you cut that paycheck in half, you still got something. You can't cut your paycheck in half over and over again and end up in negative money. You could have debt and end up in negative money, but not just by cutting your paycheck in half. So this is the famous exponential shape. What would happen? I got to add some scale here, don't I? 1, 2. 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And just for effect on the other side, I'm not gonna, well, I guess if I wanted to be fair, I would add the same numbers down here, I suppose. And your first reaction is, oh, you're wasting your time. There's nothing down there. But I'll tell you, what if I put something down there? What if we reverse all these red dots? Like this one here at 3 and 8. What would happen if I reversed it? I'd be at 8 and 3. What about this dot here at 2 and 4? What if I reversed it? I'd be at 4 and 2. It's going to be crowded if I name every point here. So I'm going to stop in a second. But if I reversed 1 and 2, I'd be at 2 and 1. If I reversed 0 and 1, I'd be at 1 and 0. Now, let's get sneaky. If I reversed -1 and 1/2, I'd be at 1/2 and -1. I'd be at, if I reverse this point, 1/4 and -2. I'd be at 1/8 and -3, and that is so close to the y-axis, it's impossible to draw. But what happens if I reverse, if I take the mirror image of that red curve? If I draw gently and carefully, I can see the mirror image. That's a perfect mirror image across the line y equals x. Over here and over here. Think about that. Are these two parts mirror images? This red part here is like becoming totally flat. What is the mirror image of totally flat? Totally vertical. You ever visited the Bonneville Salt Flats, I believe in California, where they test race cars? It's a very, very, very flat salt lake. This salt has accumulated and settled very flat there. So you're running a car at very high speeds. You're not gonna like hit a bump or a pothole in the road, and the car basically at that speed would just flip over and, you know, pop, explode basically. But what is the opposite of totally flat? Well, the opposite of totally flat is go climb a mountain, go scale a mountain that's totally vertical. These two things are inverses of each other. They're perfect mirror images. So the question is, if I know the formula of this red function, what in the world is the formula of this, as I drew it, green function? I mean, I know square roots and squares, even if I only use half of them. I know lines and other lines. You know, I got names for everything. But what's the name of this green function? This earned a special name. It's called a logarithmic function. And logarithmic is very, very old word. And basically, I guess I could look this up on Google or something, but I would say it today in plain English, like inverse power function, although I don't like that. I think you'd have to go back to Google and investigate this word, logarithm. Logarithm. It basically means undoing powers, undoing a power or inverting a power. Like you invert cubing with cube rooting, but this is not a square or a cube root. This is an x inside the power. How do you undo a variable in a power? Let me show you how people write this function. Now this function, by the way, is written. This particular green function that I drew is undoing 2 to the x. So it's written as a log base 2 of x. And when you say log base 2 of x, that's an old notation that means in English, what power turns 2 into x? When you see someone write log base 2 of x like this, when I say base, I mean I'm using this little 2 as a subscript of the log function. And I don't want to write the word logarithm. Nobody writes the word logarithm out. They just write log for short. In the same way, nobody writes out square root of 16. They just use that symbol for the square root. So when you see someone write log base 2 of x, you have to learn how to read it. What power turns 2 into x? If I said to you, and I can show you how to do this on your calculator too, we will do that. But first I got to teach you how to read it. If I said to you the log base 2 of 8, then in English, what I'm asking you is, what power turns 2 into 8? Now, you may not know immediately, but you've got some experience with 2. 2 times 2 times 2 is 8. Oh, the third power turns 2 into 8. So if someone asks you what power turns 2 into 8, you're supposed to say 3. What power turns 10 into 100? You know that 10 squared is 100, so you're supposed to say 2. Let me give you another example. What power turns 2 into 16? Now you could just work on your powers of 2. 2 to the 1 is 2, times 2 is 4, times 2 is 8, times 2 turns out to be 16. So you say to yourself, okay, what power turns 2 into 16? It's 4. Now that'll work for a little while because sometimes it's not clear what power turns 2 into a number. For example, the log base 2 of 16 is clearly 4. 4 powers of 2 is 16. But what if someone asked you, what's the log base 2 of 17? Well, you're screwed. In a way, your first reaction is that's impossible. I can't raise 2 to a power to get 17. But is it impossible? What's the log base 2 of 7? You know the log base 2 of 8 is 3. So what's power turns 2 into 7? Let's go back to your graph. 2 to the third is 8. and you want to know what power gives you 7. Well, I'll tell you what, it's got to be really close to 3, because this is very, very close to the 3 that gave me the 8, right? So let's go look up 7 on this axis, because that's got to be the same number. Very close to 3. Now, is that 2.9? Is that 2.95? Is it 2.8? You know, what power actually gives you 7? It's not going to be a clean number, but let's try 2.8. Where'd my calculator go? I have my calculator over here, and we're going to have to end it here. But let's try. Let's get out my most excellent calculator stand. 2 cubed, sorry. 2 cubed is 8. How do I get 7 instead of 8? 2 to the 2.8. Not good enough, although it's pretty darn close. That is so hard to read under that camera, isn't it? Even with my stand. That is very hard to read. Let me get more old school calculator out. 2 cubed is 8. That's a little bit easier to read. How about 2.8? 2 to the 2.8. Well, that's darn close to 7. How about 2 to the power 2.9? No, too much. In fact, way too much. What about 2 to the power 2.82? Oh, a little bit too much. How about 2 to the power 2.81? A little bit too much. 2 to the power 2.805. A little bit too low. Now, you know I'm not going to do this forever. 2 to the power 2.806. A little bit too low. 2 to the power 2.807. Oh, tantalizingly close. 2 to the power 2.808. This could get addictive. I could be going this. Okay, now I've crossed 7. So how about this? What happens if someone asks you what power turns 2 into 7? You don't really know, and we don't have time to go on, but you can tell them it's between 2.807 and 2.808. That must be this mark on this axis, somewhere around 2.807 or 2.808. Now, there's no way I could draw a picture that's accurate to the thousandths, but my calculator can calculate to the thousands and better. All I know is that actually there is a number that turns 2 into 7. I just don't know exactly what it is. It's 2.807 approximately. To the nearest thousandth, that's pretty good. Okay, we got to cut it off here. This shape is called logarithm, and it's a function that asks you for powers. Logarithm base 2 of 8 is asking you what power turns 2 into 8, what power turns 10 into 100, what power turns 2 into 16, what power turns 2 into 7. That's what this notation means. You have to get used to this notation. We're going to use it a lot. All next week, we're finishing up, and I'll help you be more familiar with it as we go along. And I'll show you how your calculator can give you a very precise approximation for any base. I've got a handout on my website showing you logarithms and logarithm rules, and I'll bring that up again next week, but we have to call it quits here. So I will post these. I'll number these and post these. See you again on Tuesday. And then we'll talk about logarithms in much more detail. So dive into the XYZ homework problems before we have to turn them in next week. And I'll show you much more about logarithms on Tuesday. Okay, you guys have a good weekend there.